In this online lecture, we're going to discuss how to predict products and major products of halogenation reactions with alkanes, ones that are a little bit more complex than what we saw in a previous online lecture. But let's talk about what we're going to learn here. Number one, we're going to see that determining the major product in an halogenation of an alkane requires a statistical method, employing the relative rates of radical formation. That'll all make sense in a second here. And number two, we would like to know that the relative rates of alkyl radical formation by Cl and Br, respectively, are Cl 5 to 3.8 to 1, Br 1600 to 82 to 1. Again, this will all make sense later. And next, we want to see that 3, the relative stabilities of alkyl radicals we should know is tertiaries are more stable than secondaries, which are more stable than primary, which are more stable than methyl. And lastly here, what we're going to see is that halogenation with Br is more selective than Cl. We should also know that F reacts too violently and I is too selective for this reaction. So we're only going to look at halogenation with Br2 and Cl2 with alkanes. Now, in a previous online lecture, remember we learned the mechanism for this reaction right here. Remember we were taught that there was an initiation step here, and that involved the halogen, in this case Cl2, reacting with either heat or light, and homolytically cleaving to give us two radical species here. And remember, these two radical species then participate in what's called a propagation step here. But notice something different is going to happen here. What I want you to see here is that technically we have a choice. For instance, let's say this is our alkane, propane. We learned before that one of these CH bonds is going to react with the Cl radical. And let's just say it happens to be the CH bond on the second carbon in this molecule. Again, the mechanism looks something like this in terms of the arrow meetup, and what we end up with as a product for this is something that looks like this. And again, remember this hydrogen right here ends up being this hydrogen right here. But what's more important right now is notice what we get here. This is a secondary radical. So what we're saying here, if that central carbon with that H reacts with the Cl radical, we will end up with a secondary radical. But that's not the only possibility. What if one of the N carbons on this molecule, let's say one of his CH bonds, reacts with the Cl radical? Again, arrow movement would look like this. He would move this way, one electron would move this way, and one electron would move on the carbon right here, and we would end up with these things as a result. Notice if this were to happen, we'd end up with a primary radical. The question is, which one of these steps is likely to happen? In order to know this, we need to know that radical stability basically mimics carbocation stability, and that is tertiary radicals are more stable than secondary, which are more stable than primary, which of course are more stable than methyl. In fact, later on we're going to be using a chart like this. This is telling us that tertiary radicals are 5 times more likely than a primary radical to form, and secondary radicals are 3.8 times more likely to form than a primary radical. We'll go into more detail about this a little bit later. However, we could answer our question right now about which pathway is more likely. Of course, if the secondary radical is more stable, then the result that leads to the secondary radical is going to be more favorable. That means, remember, when this reaction goes to completion, it is that radical that we get right here that then reacts with another Cl2 in solution that hasn't been split up. And this, of course, is the arrow movement that we get. And of course, we end up getting this right here as a product. So if you were on your orgo test and they asked you, what is the overall reaction of propane with Cl2 and lighter heat, we would say this is our major product. We'd want to put the Cl on the second carbon in this chain. And again, because we know that this results from a secondary carbocation being generated in the mechanism. So notice for this case, that's pretty easy to determine. Remember, we talked about a quick product method with this reaction before, and that was we simply replace a CH bond with a C connected to a halogen bond. What we're learning here is which CH bond to replace if we have more than one possible CH bond. However, things get a lot more trickier when we have things like this. Let's look at this sample problem here. It says, provide the major product of the following reaction. In this particular molecule, 2-methylbutane, we have more than 2 types of CH bonds in this molecule. And let's talk about the steps here that we would take to get to the answer. The first thing I would want you to do is label the different types of hydrogens that, when replaced with Cl, would lead to a given product. For instance, if I replace this A hydrogen right here with a Cl, that would lead to a certain product. However, notice if I replace the top methyl here, this A hydrogen, with a Cl, we'd end up with the same product. So that's why we're labeling both of these A. I'll show you what I mean by that in a few minutes. But keep going here. If we replace this hydrogen right here, B, with a Cl, that would lead to a given product. And of course, this hydrogen right here, either one of these two, C, being replaced would lead to a certain product. And lastly, replacing this D hydrogen with the CCl bond would lead to a given product as well. The key to being able to do this step is basically, let's get a closer look at our molecule right here. What we're quickly trying to do in our head is, again, let's replace the A hydrogen on the left here with a Cl. That would lead to a molecule like this. And notice, think about what the name of this molecule would be. The longest chain here in this molecule, again, is butane, these 4 carbons. And we have a Cl on, let's say, carbon 1, and you'd have a methyl on carbon 2. So what we're saying is if the A hydrogen were replaced with a Cl, we would get 1-chloro-2-methylbutane as a product. But notice, let's replace the other A hydrogen with a Cl. If you were to name this molecule, now this becomes the longest carbon chain, with the Cl in this case being on carbon 1, and the methyl being on carbon 2. Notice this would give the same product that we saw before, which is again 1-chloro-2-methylbutane. So that's why we're labeling both these hydrogens as A, because again, remember, when replaced with the Cl, they lead to the same product. Let's just look at one more just to make sure you got this. If we replace the B hydrogen with the Cl, you would end up with this as a product. Notice this is different from replacing the A hydrogens. Again, your longest chain would be 4 carbons long, butane, and you would have a Cl on carbon 2, and you would also have a methyl on carbon 2. So the name of this molecule would be 2-chloro-2-methylbutane. So let's go back to our method here. We've labeled the different types of hydrogens here, and here's some of the statistics that you're going to pull off. And to keep things in order here, I'm going to do it via a table. Filling in this table is going to help us predict the major product. And what we need to determine is first the H type right here. Then we want to investigate the second box here, which is the number of hydrogens that are that type. Then we want to figure out what is the relative reactivity. We're going to multiply that. And what that's going to equal to is simply the number of products. So let me show you what I mean by that. Let's start with the H type. Remember, we have 4 types of hydrogens, A, B, C, and D. So let's investigate the first type of hydrogen, the A-type hydrogen. Notice, look at our molecule. How many hydrogens are A-type? Well, there's 2 methyls there, so there's a total of 6 A-type hydrogens. That's how we fill in these boxes. Then the next thing we do is look at the reactivity level. The reactivity level involves this little chart right here that we saw before. To figure out the reactivity level of the A-type hydrogen, we simply just have to determine what type of hydrogen is the A-type hydrogen. And notice if you look there, the A hydrogens are primary hydrogens. And look at our reactivity level chart here. According to that, primary hydrogens have a reactivity level of 1. So we would fill this box in with a 1. If it were a secondary, we would fill the box in with a 3.8. If it were a tertiary hydrogen, we'd fill the box in with 5. So now to fill out this last box here, the number of products, we simply perform the calculation above, which is take the number of hydrogens, 6 in this case, and multiply it by the reactivity level, 1, and you end up getting 6. We need to do this for each type of hydrogen. So now let's do it for the B-type hydrogen. Again, filling in our chart, we're starting with the B-type hydrogen. How many B-type hydrogens are there? There's only one according to our molecule. And what is the reactivity level of that hydrogen? Well, if we look at B closely, we'll notice that he is a tertiary hydrogen. And according to our chart, tertiary hydrogens have a 5 reactivity level. Now we're ready to fill in that last box. 1 times 5 simply equals 5. Now let's do the C-type hydrogens. So starting with C, how many C-type hydrogens are there? Well, there happens to be 2 C-type hydrogens. What kind of hydrogens are they so we can figure out reactivity level? Well, the C hydrogens are secondary hydrogens, so their reactivity level is 3.8. 3.8 times the 2 equals simply 7.6. And lastly, the D-type hydrogen here, notice we have 3 of them in our molecule. And what kind of hydrogens are they? They're definitely primary type hydrogens. So primary type hydrogens have a level 1 reactivity. And of course, 3 times 1 equals 3. Notice again, this last column here is the number of products. So if you added up all these numbers right here, you'd get a total of 21.6 products. And what we're noticing here is that out of those 21.6 products, right here, 7.6, most of the products would be the one where the C-type hydrogens are replaced by a Cl. So that means, logically, if out of the 21.6 products, 7.6 of them are the C-type hydrogen being replaced, then that means that's our major product. So that means to answer this question here, the major product of this reaction is simply this molecule right here. Notice it takes a little math to pull something like this off. Notice also that we didn't get the product that you probably would have suspected. Remember, we saw before that tertiary hydrogens are more likely to be replaced with the Cl in this reaction. But that's not what we're getting. It's actually, remember, the C hydrogen that's being replaced by a Cl. That's why it's important for us to do this statistical analysis to figure out what our major product is going to be in problems like this. Now, keep in mind, you might be thinking, well, that might take a little time on an orgo exam to generate that entire chart. That's why we got to practice this. You don't have to actually create that chart on your exam. You can quickly perform these calculations to get to the major product. And the more you practice problems like this, the quicker you'll get at doing the calculations. There's something else I'd like you to notice here. There's another answer you can kind of get to from this calculation that we did. If you wanted to figure out, let's say, the percent of the products that lead to the A-type hydrogens being replaced by a Cl, then you can take this number right here, 6, the number of products, and divide it by the total. 6 divided by 21.6 is basically 28%. So what we're saying is that when you run this reaction, 28% of the products are going to be the A-type hydrogen being replaced by the Cl. You can do this for every type of hydrogen. If you take the B hydrogens, in which, remember, we get 5 products out of the 21.6, 5 divided by 21.6 ends up being 23%. You can take the 7.6 C types and divide that by 21.6, you get 35%. And 3, the last one, the D hydrogen, divided by the total, ends up being 14%. If you added up all these percentages, you would have 100%. And notice again, our math is telling us what we already know here, that 35% of the product, a majority of it, will lead to the C-type hydrogen being replaced by Cl. However, notice what happens here. Let's look at another example. Again, we got the same reactant, but this time we're reacting Br2 instead of Cl2. And remember, we know these facts again, tertiary radicals are the most stable. But this right here happens to be the reactivity level for Br. Notice it's different from Cl. In this case, tertiary hydrogens are 1,600 times more reactive than primary hydrogens. What we're noticing here is that simply Br is what they'll call more selective in this reaction. We'll go into more detail about that in a few minutes. But what I want to show you right now is that to get to quick product in this case, all we have to do is locate the tertiary hydrogen here and simply replace it with a Br. Now, how come we're able to get away with this without having to do all that math? Well, let's pretend we were actually going to do the math and watch what happens here. Again, we label our hydrogens. We got A through D type hydrogens. And let's put up our reactivity level chart here for Br. And let's do this. Let's just fill in the B row here. For the B-type hydrogens, how many B's are there? Well, again, there's only one B-type hydrogen. And what is his reactivity level? Well, since he's tertiary, his reactivity level is 1,600. Notice 1 times 1,600 is 1,600. If you were to calculate the number of products for A, C, and D hydrogens, notice you wouldn't even get anywhere near that 1,600 number, which obviously means the number of products, most of them, are going to be the B hydrogen being replaced by the Br. So this is why the math is completely unnecessary for this kind of problem. So we only do calculations when we're reacting Cl2 with an alkane. However, remember, we're shooting for mastery of organic chemistry here. So just in case, let's look at why for the Br2 reaction we don't have to do the math, and why they term this in organic chemistry, this reaction being more selective. To understand this, let's look at an energy versus reaction progress diagram. And let's say we're looking at the reaction Cl radical reacting with, let's say, this alkane right here. If these are our reactants, remember what we're saying is these reactants have a certain energy level, and for them to react, we would have to go up over an activation energy barrier and then lead to product. And in this case, our product, let's say, is simply taking off the tertiary hydrogen and replacing it with a radical. Notice this is one of our propagation steps in the mechanism. In order to pull this reaction off, we would have to get over this activation energy. However, if we reacted the Cl with another alkane, and in that process he rips off, let's say, a secondary hydrogen, then that would lead to this as a result right here. Notice the product in this case, the secondary radical, would be higher energy than the tertiary radical. Because remember, radical stability is tertiary more stable than secondary more stable than primary. So think about this. If we reacted Cl radical with a alkane that led to a primary radical, this is what it would look like. Again, product being even more higher energy. However, we should note two important things here. Notice the activation energies for all three of these reactions are approximately equal. So the rates of these formations would be roughly the same, but again, remember, since the tertiary radical is more stable, it's the more thermodynamically favored product. But the other important thing here that we want to point out is notice that means that this reaction is exothermic. And if you remember from general chemistry, exothermic reactions are typically more reactive and more likely to happen. Now, let's do the same type of analysis, but this time with the Br radical. We're going to see the energy versus reaction progress diagrams in this case are different. For instance, if the Br radical reacts with this molecule and creates a tertiary radical, this is what the graph would look like. And like we did before, if the Br radical rips off a hydrogen leading to a secondary radical, then this is what we would get. And lastly, Br radical reacting here and leading to a primary radical, this is what we would get. Notice the differences here. First of all, the activation energies are not the same. The activation energy for the first reaction is this here in green, and the activation energy for the second red reaction is here, and lastly we got the blue all the way up there to the top. These obviously are not equal, which means the rate of forming the tertiary radical is much faster, and therefore a lot more likely. which again is part of the reason why this Br reaction is a lot more selective towards replacing a tertiary hydrogen with a Br. But there's also another big important difference here. These reactions, notice, are not exothermic, they're actually endothermic. And we should remember from general chemistry that endothermic reactions are less reactive, or we can say less likely to happen. What's being revealed here is a very important principle in organic chemistry in general, and that is simply the reactivity-selectivity principle, which simply says that the greater the reactivity of a species, the less selective it will be. And remember, applying this to what we just learned, we saw that the Cl2 reaction has a greater reactivity, therefore the Cl2 reaction is less selective. And conversely, the Br2 reaction has a less reactivity, and therefore it is more selective. Notice, we don't need to know this to get to the quick product in these reactions. We're simply understanding the theory behind why the Br2 reaction is more selective. So, what have we learned here? Key points. Number one, we saw that 1. Determining the major product in halogenation of an alkane requires a statistical method employing the relative rates of radical formations, which led us to 2. The relative rates of alkyl radical formation by Cl and Br respectively are this right here in front of us. It depends on your professor if you need to memorize these. That's definitely something you might want to ask him or her. If you do have to memorize them, they're really not that hard to memorize anyway. And number 3 here, we saw that the relative stabilities of alkyl radicals, again, is tertiary, secondary, primary, methyl. And we talked about number 4, the principle that halogenation with Br is more selected than Cl. But we should also know that F2 reacts too violently and I2 is way too selective for this reaction. So that's why we only need to understand how to react an alkane with either Br2 or Cl2.